Let's next take a look at a type 1 buffering region problem. We're in the buffering region and we'd like to determine the pH. The words could look something like this. 45 milliliters of 0.300 molar acetic acid, located in the beaker down below. Well, that's titrated with 0.250 molar sodium hydroxide. And initially the burette reads 0.89 milliliters, so that's where things begin. And then we continue this titration, adding sodium hydroxide to the acetic acid until the burette reads 10.50 milliliters. And we're asked to determine, well, what's the pH of the solution going to be at that point? Now, the first thing that we should do is remember that we can always determine the volume of sodium hydroxide that's been added by subtracting the final and initial burette measurements. And in this case, we come up with 9.61 milliliters of sodium hydroxide that have been added. Where we need to go next is with a determination of the number of moles of the various contributors that we have in this particular case. The first contributor that we're going to think about is that for sodium hydroxide. Now, moles of sodium hydroxide is going to be the concentration, which we know, times the volume that we've just determined in liters, of course. And by multiplying these two numbers together, we're able to determine that 0.00240 0.25 moles of sodium hydroxide have been added as a result of this titration experiment. I'm using subscripts there to hold on to a few extra significant figures along the way. We can also determine the initial moles of the acetic acid. As we were given the volume of the solution and the concentration of the solution, the calculation is done in very much the same way, converting the 45 milliliters to liters and multiplying that by the molarity of the solution. Doing so gives us 0.013500 moles of acetic acid. Now, it's worth pointing out that in this case, recall that this is in effect a neutralization reaction. We currently have more moles of the acetic acid than we do for the sodium hydroxide. This simply means that we haven't yet reached the equivalence point, and we are indeed going to be determining a pH within the buffering region of this system. All right. Now, this is the first step in how one goes about solving problems like this. It's very important to have the number of moles of things. The next thing that we have to recall is that the neutralization is accomplished by the NaOH as it's being neutralized by the acetic acid, which is there currently in excess. And the reaction that describes this neutralization, I've written for you there on screen, shows us that we've got acetic acid and sodium hydroxide that react together to form water, which is quite typical of a neutralization reaction, as well as an aqueous salt, where we have acetate ion and sodium ions present. And in fact, we can look at the initial moles, put them in where they belong. For each of the constituents here, the acetic acid, 0.0135 moles, the sodium hydroxide, 0.0240 moles, and recall that we have fewer number of moles of NaOH than we have of the acetic acid, and this identifies the sodium hydroxide as the one that is limiting. The sodium hydroxide will be completely neutralized as a result of this, leaving behind quite a bit of excess acetic acid as a result of this neutralization. Now, what is also important about this is the products. The water that's generated is, for the most part, insignificant insofar as the total amount of water present in the solution. All of our solutions contain by far a majority of liquid water, and the small amount of liquid water produced as a result of this neutralization isn't anything that we really need to worry about. The sodium ion in this case, also produced, is a spectator and won't involve itself in any consequent, in any additional chemistry that takes place beyond this point. Now, we can track this neutralization reaction just in terms of the changes that take place. It's a bit like a material shift problem from earlier chapters in equilibrium, but now that we've identified the limiting reactant as the sodium hydroxide, we know, since it's a one-to-one reaction between that and acetic acid, that we will remove 0.00240 moles of sodium hydroxide, an equivalent amount of acetic acid, but we will also produce a small but insignificant amount of water, but an equal amount of acetate ion. as a result of this. Now, the acetate ions are important because, as we'll see later, their interaction with water does affect the pH of the system. We're not worried about the spectator ions, sodium ions at all, because after all, they are spectators, and even though they're being produced, they're not important. So as far as the neutralization reaction is concerned, we're really only worried about the fact that we have a limiting amount of sodium hydroxide. The final moles that are left at the end of all of this will have a remaining amount of acetic acid of 0.0110 moles. We'll have completely used up all of the sodium hydroxide. The sodium hydroxide has been neutralized by this weak acid, and we will have generated, as a result of this, 0.00240 moles of acetate ion. All right, so we've looked at the neutralization as it takes place when sodium hydroxide is added to this weak acid, and we have not added so much sodium hydroxide that we have overwhelmed the acetic acid. In fact, we still have acetic acid left to us. The next thing that we need to do, though, is with these moles that we've just determined, it's important for us to know what their concentrations are. And to calculate their concentrations, we, of course, need more than just the number of moles. Why, we need the volume of the solution. However, as part of this titration, the volume of the solution is no longer 45 milliliters, but is 45 milliliters plus whatever sodium hydroxide we've added. And so we'll have to calculate a new total volume before we move on to calculate any concentrations. And the new total volume will be that of the original acetic acid plus the amount of sodium hydroxide that we've added. Putting numbers in, we've got 45 milliliters plus the 9.61 milliliters of sodium hydroxide that we've added, and that gives us 54.61 milliliters, or 0.05461 liters. This is the volume now that must be used as we recalculate concentrations of various important chemical agents in this system. Let's have a look at the new concentration of the acetic acid. This will have changed because some of it got neutralized and the volume was changed as a result. And so we take the moles of the acetic acid and divide by the volume of the acetic acid solution, which is the total volume of the solution. Putting the numbers in from above, we had 0.0110 moles of acetic acid that were left, and we divide by this new total volume that we've just calculated, and we determine that the concentration of the acetic acid after this neutralization takes place is now 0.203 molar. That's down from 0.300 molar. No surprise, some of the acetic acid was neutralized, and increasing the volume also decreases the concentration. So this would be our new acetic acid concentration. But wait, there's more, because in neutralizing the acetic acid, we also generated acetate ions, and knowing their concentration is important as well. And so we calculate that in the very same way. We use the moles of acetate ion and divide by the new total volume of the solution, which we already have for the acetic acid. They share the same space, and so the number of moles that were of acetate ion that were produced, 0.00240 moles, and we divide by the volume that we previously calculated, and now we have a new concentration of acetate ion of 0.043993 molar. All right, so just to summarize, in doing a problem like this, it's best to look first at the number of moles, use the information that you have to calculate the moles of acetic acid and moles of sodium hydroxide. A quick comparison of these moles tells us whether we're still in the buffering region or not, and we are clearly in the buffering region because we haven't added enough sodium hydroxide yet to neutralize all of the acetic acid. The next step is to determine, well, what's left of the acetic acid. This is what we did in the blue region, and how much additional acetate ion we produced. And then finally, in the green region, we recognized that in order to recalculate the concentrations of these constituents, why we needed a new total volume because we've combined two different solutions, and then we recalculate these concentrations of both the acetic acid and the acetate ion using the new volume and the moles that we determined above. In the preceding slide, we looked at the neutralization of acetic acid with sodium hydroxide. We used a neutralization reaction to determine how much of the acetic acid was left, how much acetate ion was produced, and then we looked at how the new volume of the solution the combined volumes of the sodium hydroxide and the acetic acid could be used to recalculate the concentrations of important species. That was the neutralization part of this type 1 buffering region calculation. However, where we go next is now with an equilibrium problem, and the equilibrium we'll be considering is that of acetic acid interacting with water, producing in equilibrium hydronium ions and acetate ions. This equilibrium, as we solve the problem, will require us to know the equilibrium constant, which I'll give you here is 1.76 times 10 to the minus 5. And as it's an equilibrium problem, we'll use an ICE problem structure format to solve it. Now again, from the preceding slide, we calculated new concentrations for the acetic acid, and that new concentration was 0.20321. This included a reduction in the amount of acetic acid as a result of neutralization, as well as the additional volume produced by the additional sodium hydroxide. In these equilibrium problems, we're not worried about the water, as of course that's a pure liquid. Also from the preceding slide, we determined that the amount of acetate ions, 0 to begin with, is no longer 0. As a result of the neutralization, we now have a concentration of 0.043993 molar of the acetate ions, and for the purposes of this equilibrium problem, we'll assume initially that we have no hydronium ions present whatsoever. Okay, so a fairly standard ICE weak acid equilibrium problem where we can clearly see that the reaction is going to shift to the right as there's no hydronium ions, and this is going to mean that the acetic acid levels will drop slightly, and I'll use X as my variable, thereby we have negative X, and that the hydronium levels will come up by an equivalent plus X, as well the acetate ions go up as they're both products, giving us equilibrium concentrations 0.203 minus X, simply X, and 0.0439 plus X as our equilibrium concentrations. So this is the first part of the problem where we set up the ice structure using concentrations that we've determined previously in the neutralization part of the problem. Next up, we need to look at the law of mass action and go about the business of solving for a value of X. Taking our products over the reactant in this case means that we'll have on the top of this fraction X corresponding to the hydronium ion 0.0439 plus X, that'll be the acetate ion, and the only reactant that we've got is the acetic acid 0.203 minus X. And we'll be able to use the X is equal to 0 assumption in this case. We have a very small equilibrium constant favoring the reactants, and thus we don't expect a very large shift to the product side as a result. And so our X is equal to 0 assumption works in both of these locations and gives us mathematics, which are, of course, exactly what we're hoping for, very, very much simplified now that we won't have any X squared terms, and this is all going to be equal to 1.76 times 10 to the minus 5, the case of A, equilibrium constant for this weak acid. Going about the business of solving for X, we can determine, and I would encourage you to do the arithmetic, that X is equal to 8.12 times 10 to the minus 5 molar. Now, refer to the balanced chemical equation and note that X is in fact also equal to the equilibrium levels of H3O. So although we've solved for a variable X, we've also been able to determine directly that this X is the same as the hydronium ion concentration, and so now we know the hydronium ion concentration. Now, why would that be of interest to us? Well, the hydronium ion concentration, of course, is used to determine the pH of a solution. All we need is the hydronium ion concentration and an ability to take the logarithm of that value, and that's what we'll do here. The negative log, actually, of 8.12 times 10 to the minus 5 gives us a value of 4.08992, and this would be the pH of the solution. However, as you can see there, I have the 089 segment of that pH written in red digits. And the reason for that is because my calculation involved a hydronium ion concentration that had three significant figures, the 8.12 part of that, three significant figures actually, originally coming from the case of A value, which also had three significant figures, needs to be applied to my pH. However, as you should know, the pH shows all of its significant figures in the digits that follow the decimal point. And so 4.089 actually is a pH with only 3 significant figures. And I've held on to the 9.2 at the very end of that just in case I might have to do something more in terms of calculations with that value. So the value that I'd report, 4.089, or if you prefer rounding it, 4.090 would be the pH of the solution after the addition of 9.61 milliliters of sodium hydroxide. Now what we're going to do is look at the very same problem that we solved previously. However, in this particular solution, we're going to abbreviate some things to show you how you can simplify your approach and cut back on the amount of writing that you have to do to solve problems like this. Now the problem is exactly the same. We've got 45 milliliters of acetic acid, the weak acid. It's titrated with sodium hydroxide, and we've got our burette measurements that tell us that we have added 9.61 milliliters of sodium hydroxide. And the way I structure these problems is by first beginning with the moles. This is a lot like the previous solution where we determine the moles of sodium hydroxide, taking its concentration times its volume, and we determine the number of initial moles of acetic acid, taking that concentration by its volume as well. However, rather than explicitly write out the neutralization reaction, I begin with the equilibrium reaction that you see here on screen. I understand that the neutralization that takes place is going to neutralize acetic acid molecules and at the same time generate acetate ions. And rather than write that neutralization out specifically, I'm going to just remember how it all works as I organize my information beneath this equilibrium reaction. Okay, so we're going to begin with something that I call the neutralization part of the problem, where we look at the initial moles that we have. And the initial moles of the acetic acid we've determined, and the initial moles of the acetate ion before the sodium hydroxide we'll assume is equal to 0. All right? So no neutralization has taken place. But when we add sodium hydroxide, the sodium hydroxide is neutralized. And as a result of the neutralization of the sodium hydroxide, there'll be a change that takes place. And that change will serve to lower the amount of acetic acid by the same number of moles as we had for sodium hydroxide. Recall that the acetic acid is neutralizing the sodium hydroxide in a one-to-one fashion, and thus as many moles of sodium hydroxide as we throw in at this point will be neutralized by the acetic acid and will lower the number of moles of acetic acid by that same amount. That acetic acid, which is neutralized, is instantly transformed into acetate ions, and so we see a corresponding increase in the number of moles of acetate on the right-hand side. Again, I'm not showing you the water that's produced and the sodium ions and so forth that are produced as a result of this neutralization. The most important aspect of the neutralization would be the change, the lowering of the acetic acid and the increase in levels of the acetate ion, leading us to final moles. How much of these do we have once the neutralization takes place? We've calculated these values before. The acetic acid has dropped to 0.0110 and the acetate has risen to 0.00240 moles. So the neutralization step can be performed in a structured fashion immediately below the equilibrium reaction, just to serve on to conserve on space and to help simplify and speed up the solution of problems like this. Now, after we do the neutralization part of the problem, then we have to deal with the equilibrium segment of the problem, which was where we'll again employ the ICE method of solving equilibrium problems. But remember, an equilibrium problem requires that we work with concentrations. And so we'll take the 0.0110 moles of acetic acid that's left after the neutralization, and we'll divide that by the new total volume that we've previously determined by adding up the contributions of sodium hydroxide and the original acetic acid, and we'll come up with a new concentration for the acetic acid. And we do the very same thing for, well, we don't do that for the hydronium ions because in the equilibrium problem we'll assume there aren't any to start with, but we'll do that for the acetate ions as well, using the same total volume, but the number of moles that were produced as a result of neutralization, and we'll calculate its concentration like so. The equilibrium problem proceeds in much the same way as it did previously, where we recognize that things are going to shift to the right and thus generate plus x's on the right and a negative x on the left, giving us these equilibrium levels that we'll have to consider as we solve this problem using the law of mass action. All right, so we've managed to, in one page so far, include both the effects of neutralization and sketch out the equilibrium ICE problem. The only thing that remains now is for us to use the law of mass action and products over reactants to determine how these things all go together. And again, we'll be able to use our x is equal to 0 approximation, substituting the equilibrium levels for both the acetate ion and the acetic acid. And that is going to simplify our arithmetic considerably, and we'll be able to solve for a value of x, which is 9.12 times 10 to the minus fifth. And as we recognized previously, is also equal to the hydronium ion concentration. And this is what lets us solve for the pH of this solution by taking the negative log of this value and determining that the pH with 3 significant figures is 4.08994. A simplified approach to solving type 1 buffering region problems where you can structure the problem beneath the equilibrium reaction, keeping in mind that neutralization simply shifts some of the acetic acid that starts out as a reactant on the left-hand side over to the product side, and then after we've done this neutralization, the equilibrium problem proceeds in much the same way as it did previously.